Okay, everybody, welcome to lecture 2 of this series on IPAC, and I'll turn it out over to Maciej for the lecture. Thank you.
Thank you. Thank you very much. Right. So let me start. I will very quickly recall the most important definition that I gave last time. So this function is a function which is defined on the set of all Young diagrams. So what we do, we fix diagram mu, and then we want to think about this function as a function on all Young diagrams such that lambda is my variable. So whenever lambda is small, namely it's smaller than mu, I simply define this function to be 0. And whenever lambda is bigger than mu, I define it as the coefficient of the Jack symmetric polynomial in the power sum indexed by mu. And because lambda can be pretty big, then I'm just adding a bunch of ones such that the size of the index of my power sum is the same as the size of my Jack. And then there is also this combinatorial factor in front. So we call this function Jack character because when alpha is equal to 1, this is a normalized irreducible character of the symmetric group. And I also introduced this notation, which we call multi-rectangular coordinates. So whenever I have a sequence of integers which are positive and are non-increasing, so this is a sequence S, and I have another sequence of integers which are non-negative, but now they're not necessarily ordered. Then for two sequences like that, I can always define a partition. So this partition is called a multi-rectangular Young diagram. And the main problem that we would like to solve is a conjecture. So this conjecture was given by Lassalle in 2008. And the conjecture says that this Jack character, if we normalize it, then it is always a polynomial. So maybe let me just change this lambda into my multi-rectangular coordinates. So this is always a polynomial in B minus S1 minus S2, etc., R1, R2, etc., with non-negative integer coefficients. So this is the main conjecture that we would like to solve. And last time I presented a positive formula. So the positivity follows directly from the formula. However, I mentioned that integrality will be proven in a completely different way, and this is what we are going to do today. All right. So let me introduce some notation. So I introduce a new parameter gamma. So gamma is square root of alpha minus 1 minus square root of alpha. And I also need to define some formal power series. So I define a formal power series which is related to my Young diagram lambda as follows. So I take this function and what I want to do, I want to expand this function around z equal to an infinity. So then by doing this, I define some quantities related to my Young diagram lambda. So these quantities, I call them Boolean cumulants. And this is because actually they are Boolean cumulants of a certain probability measure. So this fact is not going to be very important for us, but I just want to mention that there is a relation to probability. But this equality defines me a certain infinite series of quantities. And again, we will think of them as functions on Young diagrams. So for me, this lambda can be a variable. And this identity tells me what this function, how to compute this function. And then finally, I define normalized Jack characters. And I define them by multiplying the Jack character that I defined previously by alpha to a certain power times z mu times the Jack character that I had before. So why am I doing it? Why I introduce this new variable gamma, and also I change this normalization? I will do this because it turns out that actually if we normalize everything like that, then all the computations look much nicer, and we will see some structure that is not so easy to see without such a normalization. So we will see it very soon. And the first thing that I want to do, I want to relate these functions B, these Boolean cumulants, to these multi-rectangular coordinates that I defined. So by doing this, I'm going to define two sets. So the first set is a set of so-called inner corners of a Young diagram. So it's a set given by these quantities. So here I is equal to 1, 2, etc. And there is also a set of so-called outer corners. And this set is given by these points, square root of alpha si minus a sum from j equal to 1. And now I sum up to I minus 1 rj divided by square root of alpha. And we have the following fact, which is actually just a simple computation, that if you look at the Boolean cumulant evaluated in multi-rectangular coordinates, then it is always equal to up to a sign. It is simply an elementary symmetric function evaluated on the difference of these two sets. So here, when I say a difference, I'm using so-called platistic notation. So maybe not everyone is familiar with the platistic notation. So let me quickly explain what does it mean. So this notation means that first I will define what does it mean, how to compute the power sum on this difference. So the power sum is simply a sum over elements from the first set, I to the power k, minus the sum of the elements from the second set to the power k. And then if I want to define what is this platistic notation for arbitrary symmetric function, what I do, I just expand my symmetric function f into power sum basis. So I can always do this. And then I compute each power sum on this difference. And I know how to do it because this is what I just defined. Okay. So the first the first corollary from this fact is that all these Boolean cumulants, they have a pretty easy expression in this multi-rectangular coordinates. In fact, there are homogeneous functions in S's and R's of degree L. So the idea is that we would like to express Jack characters in terms of Boolean cumulants. And if we can prove that there is an expression that involves only integers, then we're basically done with proving integrality part of Lassalle conjecture. So this is precisely what we're going to do. And in fact, we are going to find an explicit combinatorial interpretation, but not of characters in terms of Boolean cumulants, but the other way around. So we will have an explicit combinatorial interpretation of a product of arbitrary Boolean cumulants as a linear combination of Jack characters. So let L1, L2, up to Lk be some integers bigger or equal to 2. And what we have found that whenever I have a product of Boolean cumulants, then it is given by an explicit combinatorial formula involving my normalized Jack characters. And this formula is a formula that involves so-called Łukasiewicz ribbon paths. So Łukasiewicz ribbon paths are certain lattice paths that I'm going to define now. In order to do this, I need to introduce several objects. So the first object, which is called an excursion gamma of length L, this is simply a lattice path with steps of the form 1k, where k is any integer. So we always go right by 1, and then we can go either up, horizontally, or down. That starts at 0, 0, finishes at L0, and does not touch the OX axis. So now we can define a ribbon path So a ribbon path on k sides of lengths L1, L2, Lk. This is an ordered tuple of excursions. So we denote it by gamma with a vector, which is an ordered tuple of k excursions of lengths L1, L2, Lk, plus there is some extra data. So there are some possible pairings of a down step of increment S with an up step of the same increment. And we will denote set of all these ribbon paths by R of L1, L2 up to Lk. And finally, so I will finish with this definition and then I will give a big example because there are many objects here. So let me just finish the last thing is a Łukasiewicz path. So a Łukasiewicz path is just a ribbon path such that all the non-paired up steps are that they have increment 1. And these guys will be denoted by L of L1, L2, up to Lk. So this is a subset of ribbon paths. And finally, the last thing is that whenever I have a ribbon path, then I can define a certain partition. So let mu of gamma be a partition given by the increments of unpaired down steps in gamma. Okay, let me make it. So can I switch the page or should I wait a little bit? Because I finished. Okay, so I need to open a new page. Okay, so let me show you an example. So I defined several objects. So let's see what we are talking about. Okay. So I will draw the positive quadrant. So here there is a point 0, 0. And first, let me draw an excursion. So by definition, an excursion is something that, okay, I go up by 1, then maybe I go down, then I can go horizontally, I can again go up. And now what I cannot do, for instance, I cannot go here, okay? So this is not allowed. But I can go here. And let's say that I go here. This means that I finished with my excursion. So this is what is an excursion. So this excursion is of length 1, 2, 3, 4, 5, 6. So this excursion is of length 6. And then if I will have more excursions like that, then I will create a ribbon path, okay? So let me just do this. So maybe. So let me just create this ribbon path on 3 sides. So this is a ribbon path on 3 sides. I will call it gamma. So this gamma is equal to gamma 1, gamma 2, and gamma 3. So this means that this is a ribbon path on 3 sides. We can check what are the sizes. So we already know that the first one is 6. The second one is 1, 2, 3, 4, 5, 6, 7, 8. So it belongs to 6, 8, and 2. So this is a ribbon path on 3 sides of lengths 6, 8, and 2. But I said that whenever I have a ribbon path, I could possibly have some pairings. So the pairing, I didn't define them very carefully. What is important is that I always connect in a pairing, I always connect 2 steps such that the first step is a down step and the next step is an up step. So I need to find 2 steps. One is a down step, one is an up step, and they need to have the same increment. So in this particular case, this increment is equal to 2, and I am allowed to connect them, and this is a pairing. What I would not be allowed to connect is these 2 guys, because the first one is an up step. So this is not allowed. A pairing is a pairing of 2 steps such that the first step is always a down step. Okay, so this is an example of pairing, and maybe let's make one more. This is also an example of a pairing. This is a pairing of degree 1 because I connected steps of degree 1. And maybe the question for you, for the participants, is it a Łukasiewicz path? Anyone? So I will recall what's the definition of Łukasiewicz path. So I should look at the increments of the up steps. So let me just draw all these increments. So this one is of increment 2. This is of increment 2. Then this up step here is a paired up step. So I'm not looking at paired up steps. So then I have an up step of increment 1, of increment 2, and of increment 1. So the definition of Łukasiewicz path, it was a ribbon path such that all the non-paired up steps are only of increment 1. They only have increment 1. So this means that this is not a Łukasiewicz path, okay? Because in Łukasiewicz path I cannot have steps which are going high. Okay. So let me just finish this picture by adding even more colors. So I also want to remember what are the increments of the down steps. So again, non-paired down steps. So I have a down step here. I have a down step here. This is a pretty big down step. It's 4. This one is 1. This one is 1. And finally, I also have some flat steps. Okay. So for the flat steps, I will also put some numbers, but now the numbers that I will put there, it will be the height. Okay. So here I will put minus gamma. I will explain it in a second. And here I will put minus 2 times gamma. So my weight that I associate to the flat steps is always minus gamma times the height of my flat step. So for instance, this flat step is at height 1. I'm looking here. So the weight would be minus gamma times 1. Then I need to check what is the height of this. It's 2. So the weight will be minus gamma times 2. Okay. So maybe just to finish this example, I also defined this partition. So it's maybe a little bit better if I will use a color so that you will see where the partition comes from. So the partition should be violet, because what I'm looking at down steps. So this partition is given by 4, 1, 1. Okay, I'm just listing the increments of all the down steps. Okay, so is it clear what is a ribbon path?
You missed one down step.
I missed something.
Yeah.
It's
Is it
what did
three
I?
ones? Is it there are three
Oh.
ones there?
Thank you very much. Yes, that's very good. You're paying attention. So there is one. Let me check if that's all. I think so. Yes. Thank you very much. Okay, so that's good. So participants are paying attention, and hopefully everyone understands the definition. Okay, so these are the combinatorial objects that I'm interested in. And I just described that there are many statistics that you can look at when you're looking at this object. So now let me formalize it a little bit. So whenever I have a ribbon path, I can define something that I will call it an operator weight. And this is because I will associate some operator. So now I will use colors so that hopefully everyone could follow what is happening. So first of all, I'm gonna look at my red weights. So what are my red weights? It is minus I times gamma times the number of the flat steps at height I. So this is the first part of my weight. The second part of my weight is coming from pairings. So let me use a blue color. So this is alpha I to the number of pairings. So I will just make a picture like that. So I need to count how many pairings of degree I have in a picture, and I'm gonna multiply it by alpha times I. And then I'm gonna associate some operator. So I am going to multiply by pi to the number of up steps which are not paired, and they have an increment I. And finally, I'm going to multiply by, what is the missing color? It's violet. Alpha I d pi to the number of down steps of increment I. So this is one weight that I will be interested. So whenever I have a ribbon path, I can associate such an operator to a ribbon path. There's another weight which is much simpler, and this weight is actually just the scalar part of my previous weight. So, oh no, sorry. Do it again. So it is equal to this. Yes, okay, perfect. So I have these two weights. The first weight is slightly more complicated. The second weight is a little bit easier. So just to finish my example, let me finish an example. So let's just try to compute these weights. So we need to look at this picture, and again, I will use the colors so that everyone can check if I didn't make a mistake. So the operator weight, let me just compute only the operator weight because the second one is simpler. So this is minus gamma times minus 2 times gamma. This is the first factor. Then the second factor would be 2 alpha times alpha. Then the third factor is P2 to the power 3 times P1 squared. And then finally, the last factor is just, oops, it's the dp1 to the power 3 times alpha times 4 alpha d dp4. Okay, I will just show you the picture again so that you can check if I didn't make any mistake. I hope I didn't. Okay. So now we are ready to state a theorem. So here is a theorem.
Sorry, what is alpha I?
Alpha, I mean, I is a scalar. So here I take a product over I equal to 1 to an infinity. And I multiply, and alpha I is just a scalar. Alpha is also a scalar. But d dpi, this is an operator. This is a derivative with respect to pi. Okay?
But in the example, you didn't write any alpha i's, you only wrote alphas.
In an example, here I think there is alpha and there is alpha. Or am I missing something?
So it is not a subscript, it's alpha times I.
It's
It's
I
alpha
times
it's alpha times I. Alpha is
Oh,
an
it's
alpha.
yeah, maybe I times alpha is better.
Yeah.
Exactly. So maybe let me just put these little dots everywhere. Yes, it's times. It should be everywhere, okay? Alpha is a Jack parameter. So remember that we are working with Jack polynomials, and alpha is the Jack parameter that appears all over the place. Okay? Okay, so let L1, L2, Lk be some integers greater or equal to 2. And then we have the following combinatorial formula: BL1 times BL2 times BLK is given by the sum over all Łukasiewicz paths of length on k sides of lengths L1 up to Lk, weight my non-operator weight, my easier weight, which is just a scalar, times Jack character indexed by a partition mu. Okay, so this is the main combinatorial theorem that allows us to conclude integrality in Lassalle's conjecture. So before I give a proof, I will give a sketch of the proof. Corollary. Let me state an important corollary. So first of all, I can define some gradation. So if I define that the degree of the Boolean cumulant indexed by L is equal to L minus 2, and the degree of gamma is equal to 1, then first of all, we can prove that any normalized Jack character, it belongs to an algebra which is generated by the polynomial algebra generated by gamma, B2, B3, and so on. And this is precisely why, so now maybe it's more clear why I introduced this weird parameter gamma, and I changed the normalization, because now everything is really, really nice. So my normalized Jack character belongs to this algebra. And additionally, each monomial that appears in the expansion of the check character in this basis has degree equal to the size of mu minus the number of parts minus 2 times some integer. So in particular, the maximum degree is mu minus L of mu. And then the second corollary is that if I use the fact that I just showed you before, then I can conclude that this normalized check character actually belongs to this algebra. So this normalization actually suggests that the original conjecture of Lassalle could be replaced by slightly different variables. Namely, if you remember, in the conjecture of Lassalle, we had minus s's and r's, but here what naturally appears are minus s's multiplied by square root of alpha and r's divided by square root of alpha. But actually, in a conjecture of Lassalle, when in his paper, when he stated the conjecture, he said that it seems that there is some kind of natural way to express this as a polynomial in B and alpha. So even though B is not independent of alpha, because B is equal to alpha minus 1, Lassalle, he suspected that there must be some natural way of sometimes using B and sometimes using alpha. And in fact, this normalization shows us that once you normalize everything, then you have only one natural parameter. So there is no this ambiguity between B and alpha. And finally, if we add A and B, this implies integrality. Integrality in Lassalle's conjecture. So this remark basically says that actually this statement with this slightly different normalization is somehow slightly more natural than the normalization that Lassalle used originally. Okay, so now let me tell you about the proof of our theorem. So the main tool that we used are certain operators that were introduced by Nazarov and Sklianin. So first, I will define a matrix. So this matrix, it looks like that: minus gamma, minus 2 times gamma, minus 3 times gamma. This is the main diagonal. Then over diagonal, I will have P11, P11. Then here I will have P12, P12, P13, and so on. And here I will have P11 dagger, P11 dagger, P21 dagger, P21 dagger, and so on. So I hope that it is clear. Oops. Sorry. I hope that it is clear how the matrix looks like. It is stable on each diagonal. And P is equal to P1K, where K is greater or equal to 1, and P dagger is equal to PK1 dagger, where K is greater or equal to 1. And what are these operators? These operators are precisely the same operators that appeared previously, namely P1K is equal to square root of alpha minus 1 times multiplication by the power sum pk, and pk1 dagger is square root of alpha times k d dpk. Okay, so I have the same operator up to multiplication. I have the same operators as before, and what Nazarov and Sklianin proved they proved that actually they can construct operators using this matrix L and this P and P dagger that are acting on Jack polynomials such that Jack polynomials are eigenfunctions and the eigenvalues are precisely Boolean cumulants. So this is their theorem. Okay. So this is a really beautiful theorem, and it turned out it's really powerful. So now we're gonna see how we can use this theorem to prove our combinatorial interpretation.
Where is L on the left side?
So L, this is my matrix L. This is an
No,
infinite.
little L.
Oh, sorry, this is a typo. L is here.
Thank you.
Thank you. Yeah. So maybe one very small remark. When L is equal to 0, then we just multiply P times P dagger. So we basically just obtain an Euler operator. So we sum over I, and we have Pi times I ddpi. So such an operator acts on a homogeneous symmetric function simply by giving us the degree. And you can check, you can just compute B2 on lambda, that B2 on lambda is just the size of lambda. And if L is equal to 1, then it turns out that this operator is almost equal to something which is called the Laplace-Beltrami operator. So Laplace-Beltrami operator is an operator that it was known and it was proven by Richard Stanley that it acts on Jack polynomials in a very nice way. Namely, the eigenvalues are given by the sum of the alpha contents. And again, you can try to compute B3, and you will find out that this formula matches. So you could think about this theorem that this is like a huge generalization of these two facts, because now we have an infinite series of operators that are acting very nicely. Okay, so the proof. This is going to be a sketch of the proof. So first, what we want to do, we just want to compute this product, and then this product is simply this product times Jack polynomial, and then I set all the power sums in my Jack polynomial equal to 0 except for P1. And I just recall the definition of Jack polynomial. So in the definition, I had to tell you what is the normalization, because there are many choices for the normalization. And the normalization I have chosen is that precisely if I take this substitution, I've got 1. So this identity is completely trivial. I just said that PL1 times PL2 and so on times PLK times 1 is the same thing. But now I can use Nazarov-Sklianin theorem. So I can rewrite it like that. So this is PL to the L1 minus 2 P dagger, etc. PL LK minus 2 P dagger acting on J lambda. So I know how it acts exactly how I want. And then I take my specialization. So this is the first step. The second step is that now I want to interpret this operator in terms of paths. And it turns out that this operator in terms of paths is given by square root of alpha. So there will be some normalization factor, which is not so important. What is important is that this is a sum over all ribbon paths of length L1 up to Lk, square root of alpha to the number of horizontal steps in my ribbon path times the operator weight that I have defined. So where does it come from? Actually, this is not complicated. So what you should do, you should think about the definition of this PL to some power times P dagger. So you need to multiply a matrix several times by itself, and then you just try to write what is an element of such a multiplication, and this has a straightforward interpretation of paths. The only problem is that now I will have an operator which is mixing multiplication by PIs with the derivative with respect to PIs, but I would prefer to have the derivative on all the derivatives on the right-hand side and all the multiplication on the left-hand side. But of course I can do this, so I will just use the commutation relation that K d dk is just equal to K. So this is a very simple commutation relation. And this is precisely where this factor that is counting these pairings comes from. So if I use this commutation relation, I can just move all the derivative operators on the right-hand side. And whenever I do this, I actually connect some down steps with up steps. So this is a combinatorial interpretation. So this is more or less how you prove this formula. And then the first step is that now I want to see my Łukasiewicz paths. So now notice that whenever I have a ribbon path, which is not a Łukasiewicz path, then the action after substitution will be killed by my substitution. And this is precisely where this condition that I want to have only up steps of increment 1 comes from. Because if I will have an up step, which is of increment not 1, then my substitution is going to kill this factor. So that's why only Łukasiewicz paths survive. And then finally, if I have my Łukasiewicz path, then I can just compute this action. It's not very complicated. So let mu be the partition that I defined. And then what I need to understand this action of P1 to the number of up steps times a product over all i's alpha I d dpi to the number of down steps of size I. So this thing is acting on Jack, and then at the very end, I'm gonna kill all the p's which are not equal to 1. So now I can rewrite it. So first of all, I can take all the alphas that appear in front of everything. Then I will have P1 to the number of up steps times I d dpi to mi of mu, because mi of mu is precisely the number of down step, just by definition. And then this is not very hard to see that actually, if you look what this operator is doing, you will end up precisely with the definition of Jack character. So this is just a calculation that you can check yourself. Okay, so that's great. This is almost the end. So it turned out that the action of my operator gives me precisely the normalized Jack character, except that I have this prefactor. And then it turns out that actually, again, a combinatorics of these paths is really nice. So whenever I have some Łukasiewicz path, then you can check that the length of the partition plus the size of the partition is precisely equal to L1 plus LK minus number of the horizontal steps minus number of pairings. So all these prefactors simplify, and the proof is finished. So now, maybe any questions so far? I know that it was quick because it's a sketch, so I don't have time to go into details, but maybe there are some questions.
I think everyone's okay.
Okay. So now I will also give a sketch of the proof of the corollary. And this is going to be even more sketchy. But okay, so what is the most important thing is that if you perform the analysis of the structure of paths that appear, then you can conclude that whenever mu is a partition, then our formula looks like that. So if I want to take a product of Boolean cumulants indexed by the parts of this partition plus 1, this is simply the Jack character plus some smaller terms. So here, rho is smaller than mu with respect to the lexicographic order. And that's great, because then you can conclude that Jack character belongs to the algebra that you want, because the system is invertible. Okay, so we have a certain upper triangularity property, and we can invert over Z. And I'm almost done. let me just make some small conclusion. So what we have proved that we have an equality between two algebras. But it turned out that these two algebras are actually sub-algebras of a bigger algebra, which is quite important. And it's going to be important in the second part of our lectures presented by Hussein. So what is this bigger algebra? So this bigger algebra is so-called algebra of shifted symmetric functions. So I will finish with the definition and with an abstract characterization of Jack characters that is quite important for the proof of the combinatorial, positive combinatorial formula. So suppose that we have a polynomial over rational functions over square root of alpha, and we call this polynomial a shifted symmetric polynomial if f is symmetric in shifted variables. So Si minus I divided by alpha. And then we can define a shifted symmetric function. We do precisely the same thing what we do with symmetric functions. So essentially, this is just a projective limit. So a shifted symmetric function of degree m. This is just a sequence of shifted symmetric polynomials such that the degree of fk is equal to n for k large enough, and fk is shifted symmetric in k variables. And we have a compatibility relation. So if I take fk plus 1 and I kill the last variable, then I will get my fk. So the last theorem, I will finish this lecture by stating a theorem. So the theorem was proven by Valentin Ferret, which is a characterization of Jack characters. So a Jack character is the unique element of the algebra of shifted symmetric functions such that the first condition is that the degree of theta is equal to mu, and the top degree part, the homogeneous top degree part, is given by alpha to some power times a power sum. And the second condition is a vanishing condition. So whenever you try to compute what is happening on a small Yang diagram, and we actually have already seen this condition, then you always get 0. So let me just finish with the last remark. So the main idea to prove the combinatorial formula, the positive combinatorial formula for Jack characters that involves maps, is to just check that it satisfies these two conditions. So that this is a shifted symmetric function, that the top degree is what you want, and that it vanishes. And once you know it, thanks to this theorem, you know that it must be equal to your Jack character. So this is the main idea, and this is what Hussein is going to present in the following lectures. So thank you very much for listening.
All right, great. Anyone have any questions? Maciej.
I do have server. I
Okay.
have that
Okay.
again. Sorry. Yeah, so it's more like the motivation thing. So it's like just now you said that like you have this shifted like a shiftment, right? So that you fit everything really well. So how like is it like a normal thing to look at, like the how to shift it, or is actually something like is there something like people usually do, or is something that you have to really try? Like how do you find that shift?
So, okay, so actually this idea of working with shifted symmetric function, I'm not sure if Knopp and Sahi were first people who tried this, but at a very similar time, Knopp and Sahi, but also Olshansky and Okunkov, they were using this kind of idea to understand Jack and McDonald polynomials by defining this kind of shifted Jack polynomials. And it is very useful because of this vanishing condition. So they have this nice condition that you check that your function vanishes on a certain set, and then you are basically sure that this is the function, this is the unique function that you want to find. So as far as I know, I don't know if in the context of Jack and McDonald polynomials, someone else was doing it even before them, but they did it, and their papers are from the
Yeah,
90s, so
that
20,
that I was
20,
yeah
30
I
years
know
ago.
30 years ago. Yeah, I am aware of like their work, but I'm just like wondering if there's like any insight on like why people look at this shift. I know like it's like, oh, that works, but it's like, how was the motivation? If you ask me to suddenly think about the shift, I would not have come up with that.
Uh-huh.
So I was
can-
just thinking about why.
If I can maybe jump in and answer this
Yeah,
question.
yeah, great.
Sure.
Yeah. So, I mean, these the shifts showed up in some work that I did with Bertram Costand, which was before I understood that they had anything to do with McDonald polynomials or Jack polynomials. It had to do with these Capelli operators, which are invariant differential operators. And in this situation, the shift shows up naturally. It's the what's in Lie theory called the row shift, which shows up in something called the Hirschchandler homomorphism. And
Okay.
that's how the row shift came up. And then, it had it turned out to have very nice connections with Jack polynomials and McDonald polynomials. Because
I
Jack
see.
and McDonald polynomials, among their, millions of marvelous properties, one of the things is that they do generalize spherical functions, which is how actually McDonald got interested in them.
I see.
The row shift is kind of natural, but there was no reason why it should have this sort of combinatorial, completely combinatorial incarnation, but it does.
That's amazing. That I didn't really know. Wow.
So
Yeah,
in
and
our, if I
yeah.
can add something, so in our context, basically the problem is that all the connection with maps that is known, it is always due to the representation theory. So for alpha equal to 1, you can use representation theory of the symmetric group, and for alpha equal to 2, you can use a representation theory of the Gelfand pair. And then, so first you use representation theory, then you use a fact that you can encode maps using some other combinatorial objects that are strictly related to the representation theory that you're working on. But if we want to prove something similar for arbitrary alpha, then we basically we don't have these tools at all. So we need something completely different. And it just turned out that this characterization is very helpful. So if you are able to figure out what is a potential candidate for your combinatorial interpretation, and then you want to prove it, then it just turned out that you can use this abstract characterization to prove it. But it's complicated. It's complicated. So you will see when Hussein will show that actually checking these conditions, that this generating series of maps that gives you a positive formula for your Jack character, checking that this generating series satisfies these conditions related to the structure of shifted symmetric functions, it's quite complicated.
I see. Okay. Another question that I have is actually back to the paths. So I'm not familiar with the ribbon paths. This is almost like the first time I'm like, I have similar things, right? But I don't actually really know it. So for the maps, like, so the matching, so is it like if you match so for different matching gives you different statistics, correct? Because seems like everything when you're looking at the statistics, it depends on whether the things are matched or not. And it seems like the matching is like chosen by us instead of like fixed by the path. Am I understanding correctly?
Yes. So I mean, so when I said that you sum over all ribbon paths, this means that you sum over all paths with possibly all possible pairings. So you are looking in all possible ways you can add a pairing such that it satisfies the constraints, namely that you need to match two steps such that the first step is a down step, the second step is the up step, and their increment is the same. So for a fixed path, you can of course do it in finitely many ways. So you have a fixed path, you look at all possible possibilities, and these are all the objects that you are counting. And for each such an object, the weight will be different, right? Because the operator part will be smaller. Namely, you don't multiply by pi, and you don't have the ddpi that comes from these two steps that you just matched. But you only have your scalar, which is just k times alpha.
I see. Yeah, I'm like quite interested in that. So like, another question that's not really related, but is related to the path but not related to Jack, is that like, what if like people have multiple paths like this, and then like things like crossing, if they have crossing, like say for example you have two ribbon paths, and then they may be nesting about each other, or if they are not nesting above each other, like are these objects something that is like studied, and then like what is the relation between other things if you have nested or maybe non-nested with crossing paths like that?
So this is actually a very good question, and one thing that we at the moment do not understand is how to directly relate these ribbon paths with maps. So there should be a way somehow, and there are many properties that seem to be very similar. So for instance, we have this genus expansion of maps, and it turns out that if you look at these paths, the number of pairings in a like I won't be precise at the moment, but it seems like the number of pairings has to do something with genus. So if you don't have any pairings, this is like a planar stuff. If you have more pairings, this is like a higher genus stuff. But everything that I'm saying is speculative, because in fact we do not have a direct connection between these paths and maps. Maybe if one day someone will be able to find it, then there will be a new proof of this theorem that we do not have to check all these all these conditions related to shifted symmetric functions. So this is very speculative, but it seems that a lot of structure of these ribbon paths is similar to maps, but
I
we
see.
really don't understand it at the
Interesting.
moment.
All right, thank you. These are all my questions for now.
Any other questions? I did have one
Uh,
comment, kind of a big picture comment. So for those of us who work mainly with McDonald polynomials, so Jack polynomials have always been connected closely to a statistical mechanic kind of combinatorics. But McDonald polynomials not quite. And very recently, Maciej and Michele Diodario in a joint preprint have a way of introducing these theta operators, which arose in the study of the delta conjecture and modified McDonald polynomials. And they apply those to get McDonald versions of Lassalle's conjecture, which, you know, positivity and all these variables with another parameter. And so, and other versions of these jacks. So that makes these lectures, I think, very timely. Well, there's no other comments or questions. We'll adjourn for today.
sorry, I have a question.
Yeah,
Okay.
A
go ahead.
short question. It's about this Nazarov theorem. It looks like integrable hierarchy. Is it correct? And is it the
Yes.
connection known or?
So what they call it, they actually call it a quantum Benjamin Ono hierarchy. And this is because there is a classical Benjamin Ono hierarchy, and this one looks like a one parameter deformation. So I can't tell you what are the what is the interpretation, like a physical interpretation in terms of mathematical physics. But I do know that this is an integrable hierarchy, which can be thought of as a one parameter deformation of the classical Benjamin Ono hierarchy.
Thanks a lot.
Anything else? Okay.
So actually, I do have
Oh.
one,
Okay.
if I may. No, but if
Yeah,
it's
go
getting
ahead.
late.
No, you're fine. Go ahead.
So this Nazarov's-Klianin paper, I mean, another way to construct these operators, which have jacks and McDonald as eigenfunctions, is using the Hecke algebras. So is there some Hecke algebra understanding of the Nazarov's-Klianin story?
So I'm not really sure. So as far as I understand, the operators that you construct using Hecke algebra, they're more related to the monomial basis. So so they do not look quite the same. And even though some differences are really subtle, it really matters for us that we have a differential operator that is that has a natural interpretation in terms of power sums. And I mean, of course, because of the problem that we're trying to solve, and the problem is about the power sum expansion. So that's why. But if you're trying to, so there are many different operators that are acting on either Jack or on McDonald in a nice way, such that Jack or McDonald are eigenfunctions. They're all kind of very closely related to each other, but there are these subtle differences, and sometimes these differences really matter. So in this particular case, I do not really know how to obtain these operators directly from Hecke algebra.
I mean, it's a good answer because Hecke algebra has been around for a while, and Lassalle's conjecture kind of didn't yield to Hecke algebra techniques. So yeah, I mean, this is the right algebra, I guess.
Okay. Last chance for a question. Going, gone. Okay. So we'll adjourn for today and see you all on Tuesday. Have a great weekend. So long.
Thank
Bye-bye.
you. Bye.
Bye bye.